Okay, so hello everyone. Uh, uh, let's start. There's one technical announcement that tomorrow there will be two lectures in advanced geometry, and there will be another such exchange. I forgot, probably on 31st of October, if it makes sense. Uh, because originally we had four lectures of mathematical physics. So I want to ask, are there any questions about what was going on the last times, or about the problems in that list? Hmm? Hmm? Mhm. It depends on what. It depends on how you define the Fourier transform. Because when we talk about circle, then functions should be periodic with some period. They can be discontinuous, but still periodic. So if you have a function of x plus 1 equals to function of x, then it means that this function should be given as a sum uh, from over integer n's f tilde n e to the 2 pi I n x, and so this fn tilde is equal to integral from 0 to 1 dx f of x e to minus 2 pi I n x. If you put, if you make it L periodic, for example, if you put here L, then what should be modified? We should divide here by L, right? Also here by L, so that function is L periodic. And what else should be changed? So if you suppose that there is such formula, then what should be changed in this formula? Can you just guess immediately? Hmm? Yeah, yes, this for sure. And what else? Hmm. Hmm? Yes, so dx over L here. So, hmm? So for example, another natural choice is to consider 2 pi periodic functions. In this case, in this exponentials will not contain 2 pi, but in this case, you need to divide by 2 pi. Mhm. So, but why didn't this question appear? Because I missed somewhere 1 and 2 pi in the problems, or not. So, in a sense, either some mistake in the problems, or it was just an abstract question. Mm. 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 Ah, I see. Mm. Mhm. Oh, but by default, if I write some function that has period 1, then of course idea is that it should be expanded in such kind of series. Because in principle you can say that you cut this function at some other number, it becomes discontinuous, and you can expand this discontinuous function as a Fourier series. But it's not a very natural problem. So, well, so sometimes it's natural, but usually it would be just a mistake. Oh, other questions? Uh, so shall we continue? Or do you want? Yeah. Uh, yeah. So last time we were talking about um, generalized functions. Uh, so uh, uh, they are functionals on the space uh, of some good functions, and usually uh, people take C infinity functions with a compact support, uh, so that we can compute a pairing between uh, between generalized functions and some C infinity with compact support, and it will be some well-defined number in R or in C. It doesn't matter. And by the way, there was a question if there is this definition uh, and uh, mm, examples of such functions are, for example, delta function. So pairing of a delta function with an arbitrary function. So maybe zeros example. Uh, so zeros example is an example of unusual functions. In this case, this action is given just by integral f phi. mm, There is an example of delta function. Mm, So delta with phi uh, will be phi of 0 by definition. We also saw an example of principal of this principal value. So limit to 0. But these examples. But if we want more, we can uh, we can write, for example, something like this: nth derivative of the delta function. So nth derivative of the delta function paired with some test function should equal to something. So if you want to postulate it somehow, what would you choose here? Hmm? The question is, we have the definition of a delta function, right? In principle, if it were just the usual function, we would do what? We would integrate it by parts and then compute pairing with the delta function. But what to do with this generalized function? Like what should be the natural definition here? Almost because yes, but with some yes minus 1 to power n, yes. This is because the integral of because pairing between f and f prime and f prime and phi equals to integral from minus infinity to plus infinity uh, f prime phi dx. So it is f phi from minus to plus infinity, which is 0 because phi has compact support. So you see, this can be important in such situations, but in general it may be too restrictive. So minus integral of f phi prime dx. So it equals to minus f phi prime. So when you uh, move one derivative from one term to another one, it gives a minus sign. And if you do it n times, it will give minus 1 to the n. Okay. So, and are there some questions? Because it's we compute difference between its value at plus infinity and at minus infinity, and if we impose this restrictive condition that phi should be with compact support, it means that it is 0 at infinity. So compact support means that it is non-zero on some compact subset of R. So it's definitely 0 at plus and minus infinity. So it's just 0 on both boundaries. Or okay. So in general, so even if it is not non-zero, we can always ask this function to be decaying fast enough at plus and minus infinity. So, mm, and uh, mm, So what else? And we obtained all these functions as some sequences of the usual functions that converged to them. So uh, uh, mm, mm, convergence. So it's called convergence. Uh, so uh, some sequence, for example, delta epsilon or f epsilon converges to f. It is the same as for any phi in this C, C infinity with compact support. F epsilon f epsilon phi converges to f phi. And we saw examples of such sequences. So there was delta epsilon. So one option for delta epsilon was epsilon over pi x squared plus epsilon squared, or yes. Mm, Another option it can be even even more decaying. It will be something like e to minus x squared over epsilon over square root of p epsilon. Oh, no. Sorry. Square root of well, just better do like this. Epsilon over square root of, of pi epsilon squared. So it is some function, some Gaussian of with epsilon, and mm, well, it is a bad picture. It's more like this one. So there are such examples, and of course, if you want to get such sequence which would describe some derivative of delta, you can just take any of the sequences and differentiate it. So it will be something which you can look at. Mm. And by the way, such functions appeared as, at least in our situation, they appeared as Fourier transformations of something. So, who remembers what is the Fourier transform of this function? So, what if we compute delta tilde epsilon of x? What will it be? Mm. Mm-hmm. Yes. Sorry, it will be p. Yeah, thanks. So, so it is easier to remember because this function is decaying at infinity quite slowly, which means that Fourier transform should be discontinuous. And also know that Fourier transform of just delta function without epsilon will be just 1. So we need uh, to find some function that goes to 1 and decays is discontinuous at 0, but decays at infinity. By the way, who can guess the Fourier transform for this function? For example, did you compute Gaussian integrals at any moment?
Should be maybe the same function or something like it. Maybe epsilon squared p squared.
Yes,
See, see, see.
but I'll show how to compute this. Uh, so minus epsilon squared p squared. So the difference between this function is that this one is continuous at 0 because this function was decaying very fast at plus and minus infinity, and it's also decaying at infinity because this function was continuous. And if you want to compute this, then we need to do what? Compute the integral from minus infinity to plus infinity dx e to the I p x. I'm actually forgetting this signs. Probably it is minus in this case. So now we want to collect the full square here. Dx e to minus x plus what? Plus I p over ip times epsilon squared over epsilon squared ip epsilon squared actually. So if you 1/2. So if you open this square, then we will see precisely this minus ipx. And there is one term which we should add to cancel p squared term. This will be minus so actually there is a prefactor 1/4 here. So this term, and there is also the term epsilon over square root of p pi. So how to compute this integral? It is we would like to shift integration contour to remove this constant shift in x, and we can actually do this because it is some imaginary shift. So originally our control was here, and we would like to shift it in the negative direction. And it is possible because if we interpolate between these two contours somewhere the distance r, then value of this function at this distance will be approximately, so e to this squared over epsilon squared will be approximately e to minus r squared over epsilon squared. So it goes to zero with very fast with, with a huge rate. So we can send this r to infinity and get the integral over the shifted line. So it will be just epsilon over square root of pi, integral from minus infinity to plus infinity, and dx e to minus x squared over epsilon squared times e to minus 1/4 p squared epsilon squared. And this integral can be computed. It equals to 1. So the Fourier transform is this. So is it fine? There is another epsilon sequence. And by the way, last time there was a question if it is true that any generalized function has some sequence of usual functions that converges to it. And the answer is yes, precisely. Because we have such kind of approximations of delta functions. Because so uh, we can take we can define epsilon of y by the pairing between f uh, between f and this delta sequence epsilon over square root of pi e to minus x minus y squared over epsilon squared. So it's not quite an C infinity with compact support, but it decays at infinity with a huge rate, and in principle we can just send it to zero after some value of x. So we can interpolate it in this way to zero, but the idea will be absolutely the same. So we can consider a kind of a smoothed version of any generalized function. And if we now try to integrate this f epsilon of y with some function phi, so integral of so so it will be the integral from minus infinity to plus infinity. Uh, so let me write it like this. this converges to just phi. So this converges to f f phi. So of course it should be done more carefully. We should take care about the rates of convergence and so on. But in general, idea can be this. Or we can also say, um, probably we don't study enough the properties of the Fourier transform, but we can check that um, this so integration with such a kernel is kind of smoothing of a function on one side, and on the other side it is a multiplication of the of its Fourier image by the Fourier image of this function. Mm. So. Uh, so this can be treated as some smooth version of the generalized function. Mm. By the way, let us study this phenomenon. Namely, let us ask what happens if we multiply two functions and they then take the Fourier transform, or if we multiply Fourier images of functions and then take the inverse Fourier transform. So, but by the way, are there any questions about this idea? Hmm? Uh, so. Hmm? Yes. We can write that originally it was the integral. It was this integral. But when I write this pairing, it means a pairing of these functions as function of x. So. So uh, so since it is a function of x and we integrate in y and everything is linear, we can write it as a pairing of the integral with the function f. So, and now this converges to phi of x, and this so this converges to f phi. So is it better or not? So this integral can be treated as an infinite sum for different values of x. So and so we can say that first compute this integral with phi, and then compute a pairing with f. So it's like f was mm, uh, was mm, maybe. mm, No, probably I should have written it. No, it's already. I wrote the same integral twice, I think. So it originally it was like this, and then I said that uh, that uh, sum of fi's paired with phi is the same as uh, mm, no, it's a wrong analogy. Mm, so it is like this. We have some function f which pairs with some Cij's, uh, and this is summed over, let us write Cxy, sum over y, phi y. And then it is on the left side, and on the right side I say that it is f paired with the sum of Cxy, phi y, right? So sum and integral is almost the same from the point of view of linear algebra. Hmm? Yes. So there you. Uh, yes, we check that these functions converge to f in the sense of convergence. Because they remind me of the procedure to compute the coefficient of with transform or something else with like e to the power of minus a I and x to the other. So I was wondering if they have a particular name or something. I don't know. So. Um, So I would so the name for such procedure is a convolution, but uh, mm, mm, uh, mm, and this can be called as kind of smoothing of this function. Mm. But it's definitely not about the computation of the Fourier transform. The only relation to the Fourier transform is that the action of such operation in the Fourier space is simpler. And this is what I want to tell. Mm. So this also appears in the heat equation. So this transformation is in the action of the heat equation in the time epsilon squared, maybe 4 epsilon squared, but I will come to this at some moment later. Okay, but so are there any other questions? Okay, so maybe the next short topic, which is called Fourier transform and convolution. So, namely, there is the following question. So, suppose we have some functions f and g, or big F and big G. So function f has a Fourier transform f tilde. So f of x, f tilde of p. Function g has a Fourier transform g tilde of p. The question is, what is the Fourier transform of f of x, g of x? So let me write the answer. So in principle, we can just define it like this and then compute another definition of this. So it is called convolution. The star is called convolution. So, we can compute what it is because if for image of of x is f tilde, then f of x is the integral in dp over 2 pi. So I'm writing this for the Fourier transform on a line, but this can be done also for this Fourier transform in a circle, or even for the for finite Fourier transform on a finite set. The idea will be actually the same. So this one, second one. And here I can use some different no, here it should be, this letter should be the same, but I use different letter for the integral, just to have it in more convenient form of p. So now let us compute their product and then compute the inverse transform. Hmm? Thank you. Yes. Mm-hmm. So, thank you. I should have done it. Mm. So, the Fourier image, which is by construction f star g tilde of p. It is by construction the integral from minus infinity to plus infinity dx e to minus I p x f of x g of x. So we say that it is a Fourier transform of a product. Now let us substitute these two integral representations. So it will be dx all integrals from minus to plus infinity. dp over 2p to pi prime over. And here let us write all the terms. G of p, g. Well, actually, sorry, I actually wrote this. I wrote this convolution in the wrong way. It is convolution of the Fourier transforms. Sorry, it's not a single tilde, but tilde about each letter, like this. And also this argument should be p with two primes, because otherwise it will coincide with one of the integration variables. Yes, so it will be minus e I p with two primes. So let us now collect all these exponents. So it is I x. So this first integral brings p. Second integral brings p prime. And this integral brings minus p two primes. Right? Hmm? Because it is a mistake. Sorry. And the first one is f. Sorry. Hmm.
The convolution of f tilde g tilde, it should be that's the transform of the product.
It's a transform of it's a by definition so the convolution is not defined yet. I'm saying that there is some procedure which is which constructs Fourier transform of a product in terms of Fourier transforms of original functions, and I want to find what it is. So maybe the correct notation should be this. So there is some procedure, some operation done with these functions and then computed at point P. So it is some function. Okay, you see that one of these integrals can be computed. Hmm? Yes, and this always sometimes people write it as a single integral. But in principle we can write three of them here. Hmm? So so sometimes people omit all the integrals if it is clear that we get some number and not a differential form. So if you leave one of the variables unintegrated, then of course we should write which integrals are computed, which are not. Okay, so but who knows how to compute at least one of these integrals? So which one can be computed now? Yes. And what does it equal to? Hmm. Mm, 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 mhm. Uh, no, but this. Mm, mhm. Yeah. Yes. Mhm. Well, of the argument. So yes, it's correct. So there is all this part which we had originally. Mm. Tilde of p g tilde of p prime, and this integral dx of this exponential is to p to pi times delta function of p plus p prime minus p with two primes, right? So, hmm? 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 Uh, there are different ways to remember this. One way is to compute this integral as so we can compute it as integral minus infinity to plus infinity dx e to minus epsilon x epsilon absolute value of x e to I x some z some no, I x some z for real z. See that it equals to this delta sequence that first one, yes, this one, to epsilon over x squared plus epsilon squared, and then check that it is 2 pi times delta epsilon of x. So it's one way. Another way is the following. So if you trust in such kind of computations, and you know that Fourier transform and inverse Fourier transform are actually inverse to each other, you can imagine that you are computing the Fourier transform of the delta function. So imagine that this function so which one do we need? Right, yeah, in this direction. So this function is a delta function, right? Uh, then if you compute Fourier transform of the delta function, it will equal to 1 over 2 pi, right? Uh, because it is just value of this exponent at 0, right? And then you can take the inverse Fourier transform of 1 over 2 pi. It will be delta function, but at the same time it is the same integral which we are computing. Uh, so uh, so one, let us write like this: Fourier transform of delta function of uh, of x is the integral. So in which direction? No, let us do like this. So Fourier transform of the delta function is uh, the integral in dx e to the minus I p x delta of x minus infinity to plus infinity. So it equals what does it equal to? So how to compute this? Yes, because it is e to the I uh, px computed at x equals to 0. So it is 1. Right? And so if you so now you want to compute the inverse transform of this one Fourier transform of x. So this tilde is actually knows about the context, so whether it is a direct or inverse Fourier transform. Mm. Uh, so, well, maybe let us better write that it is the delta of x reconstructed from its Fourier transform. So we need to compute the inverse Fourier transform minus infinity to plus infinity. Mm, mm, d over 2 pi e to I p ipx times 1. So this is precisely the integral of our interest. So it's a way to remember this coefficient 2 pi, for example. So, so is it an explanation or not? So are there any other questions? Okay, so we have this integral now, and we can compute one other integral because like, and all these integrals can be computed because it is just a delta function. So we can uh, compute, for example, an integral in p prime. So it will uh, express p prime in terms of p two primes and p, and then give. Uh, so we cancel this to pi. So it gives the integral of d p over 2 pi f tilde of p f g tilde of p with 2 primes minus p. Uh, so it's the definition of some convolution we were looking for. Actually, it is with so there is this 1/2 pi in the definition, and usually when people write convolution, they write it without this. So, for example, if it is a convolution in the coordinate space, it would be just the integral in dp. Or maybe I can, or we can say that a measure in the momentum space is always dp over 2 pi, and it is a reasonable choice. So, and now looking at this formula, we can check what happens if you multiply Fourier image of a function by 1. So on one side it changes nothing, On the other side, we need to multiply it by 2 pi times delta function. And so, so example. So g of mm, so example, g of x is 1. So multiplication by g will give nothing. Mm, actually, uh, uh, g tilde of x of p equals to pi times delta function of p. So now compute for arbitrary function f tilde with g tilde of p2 primes. So this integral can be computed again, and it gives g tilde of p 2 primes. So as it should be, multiplication by 1, it changes nothing. Yes, sorry, yes, it is f. Mhm. Yeah. So, and the same works, of course, in the opposite direction. So, if we multiply functions in the Fourier space, probably I can erase this. Check. So here we had this second that f corresponded to f uh, f tilde f x corresponding to f tilde of p, uh, g of x mm, corresponding to g tilde of p, and if we now multiply for images like uh, mm, then f of f convolution with g of x will correspond to the product of their Fourier images. So in this case, this convolution in the coordinate space will be given just by a usual integral without any 2 pi's. So So it's of y. So we can check it precisely in the same way. Mm, so yes, so the general rule is that if you have integration in p, then it always comes with a factor 1 over 2 pi. If it is integration in coordinate space, it is always integration in dx. So, but you can just compute this formula. So the difference will be that this first integral will contain 1 over 2 pi, and these two integrals will not contain it. So the final answer will be with dx instead of dp. And so uh, uh, I'm writing this in particular to explain the meaning of such formulas when we compute pairing of some function and something of this kind. So if f is the ordinary function, then we have formula like some f epsilon of x uh, f epsilon of x equals to the integral from minus infinity to plus infinity dx epsilon over square root of pi e to minus x minus y squared over epsilon squared times f of x. So what is written there? So in the case when f is the ordinary function, not generalized one, it is literally the convolution between f and uh, this function epsilon over square root of pi e to minus x squared over epsilon squared. So if we write the same in the Fourier, if we write the same for the Fourier images, then we will have that f epsilon tilde equals to f tilde times times Fourier transform of this epsilon over square root of pi e to minus x squared over epsilon squared. So in this Fourier transform, we already computed this. It equals to e to minus epsilon squared over 4 p squared. Hmm?
Epsilon next shouldn't be f of epsilon epsilon.
It's of y actually. Sorry. Hmm? Is it fine or?
Yeah.
Mhm. Yes. Okay, so the main message of all this that is that if we multiply something in the Fourier space, then after the Fourier transformation, it turns into the convolution. This was one application of this knowledge. We know that convolution with such Gaussian function is a multiplication of the Fourier image of a function by different Gaussian. So if you had some function that had a non-trivial Fourier image, for example, it could be growing at infinity, because, for example, let us compute the Fourier transform of the derivative of a delta function. How will it behave? Delta n tilde of p. So it will be integral from minus infinity to plus infinity dx. Let us write by definition. So it will be pairing between delta function delta n and e to minus I px. So it was by definition minus 1 to the n d over dx n e to minus I p x at x equals to 0. So when we take this nth derivative, it will be minus ip to the n times minus 1. So it will be ip to the n. So see that it is something that goes to infinity at infinities, and if you try to substitute into the Fourier transform naively, it will produce some problems. But if we apply this smoothing to such function, it multiplies its Fourier image by something that goes to 0 with a huge speed, and this becomes some well-defined function. We can take the inverse Fourier transform of it, for example. So is it okay? And in general, we see that when we compute such a convolution, functions which were not continuous, for example, immediately become C infinity functions, because asymptotics of their Fourier transform at infinity is exponential, or even faster than exponential. Okay. Okay, let us find some more useful application of this knowledge about the convolution. So last time I proposed the following idea to solve the wave equation. So we had the wave equation, which was uxx or utt t minus uxx um, equals to some function. So we add some function to the right hand side, f of t and x. And the idea was that we can substitute the Fourier transform of these functions instead of functions themselves, like this. So u of t and x can be represented as d omega d p over 2 pi squared e to minus I omega t plus I px. So it's kind of Minkowski scalar product, and people use sign convention where uh, omega and t appear as minus I omega t in the integral in omega. But it can be chosen in really in the arbitrary way. So you tilde of omega and p, and the same for f. So and when we substitute this, we find that u tilde of um, omega and p times minus omega squared plus p squared equals to f tilde of omega and p. So now we would like to say that this so this u tilde of omega and p is let us say it let us call it j tilde of omega and p times f tilde of omega and p. And this j tilde, j tilde, or its Fourier transform is called green function. So let us write this formula in the coordinate space. Hmm? Well, I will green function, but I will write it. So we see that here, so it is some naive calculation at the moment. It should be made precise. But the idea is this: we have multiplication of two functions in the Fourier space. So if you go to the coordinate space, then it means that u of t and x will be given by the integral in some t prime dt prime in dx prime um, from minus infinity to plus infinity in both of them. Uh, g of t minus t prime, x minus x prime, f of t prime and x prime. And this object is called green function. Uh, uh, are there any questions about this?
This procedure, how how it affects the pattern recognition, if there are some pattern recognition.
It's a very good question, which we will discuss later. So it's important because in principle what is written here at the moment makes no sense because this G tilde has a pose for some real values of omega and p, and so it's a quite a bad object. It would be better if we put here omega squared plus omega squared plus p squared plus m squared to be on absolute safe side. In this case, there will be no problem. We would be able to compute this integral. And it would be a well-defined function. But here it's, and it is related to this question about boundary conditions, because here we solve this equation for arbitrary right-hand side, but we don't say neither the domain where this equation is satisfied, nor conditions at infinity, because so suppose that we have one solution of this equation. We can just take this solution and add here and add to it arbitrary combination of some functions of t minus x and t plus x. So u of t and x is the same as u of t and x plus some f plus of t plus x plus f minus of t minus x. So if it is a solution, then this is also a solution. So so if we don't say anything about boundary conditions, then this solution is not uniquely defined. And by the way, there is also a question about existence and uniqueness of solution of this equation. And we are basically proving existence because we will just write a formula for this solution. And then we will spend some time on uniqueness because it involves some new ideas about energy conservation and so on. So it's some separate topic. But at this stage, we see that there is some huge problem of uniqueness before we decide something about the boundary or initial conditions. And let us try to solve this problem in the following way. So. Oh, blech, I can erase this. Okay, so the true formulation. So we should say that so u of t and x is defined for t greater or equal than 0, x from minus infinity to plus infinity. Actually, we can, well, maybe better to put some minus big T. To be not very restrictive, but it's the same up to some translational symmetry. And we say that u of minus t and x equals u t of minus t and x and equals to 0. So we fix initial conditions to be 0. But in principle, it does not restrict anything, because if we want to solve equation with some initial conditions, we just add a solution with 0 right-hand side to our solution. So we know how to solve that equation, and we can just sum them. So problem with initial conditions and problem with the right-hand side are independent. So we can solve them one by one, and we know how to solve one of them. So we want now to solve this problem. And if so to satisfy and you see that if this green function is non-zero for any values of t and x, then we can easily evaluate this condition. So we want to find a gain function which would be 0. And by the way, since we are considering this domain for u, we can also say that this function f in the right hand side of t and x is is equal to 0 when t is less than minus t. So so if we find the green function such that it vanishes for a negative time, so if it vanishes for a negative time, then it would mean that u of t and x will satisfy this initial condition. Because so in this case, u of minus t and x will equal to the integral from minus infinity to plus infinity d dx g of g of minus t plus t prime minus t prime minus x prime f of t prime x prime. So on this integral in t prime will go from minus minus t to plus infinity. X integral is from minus infinity to plus infinity. So so this g will vanish everywhere except some line, but it's integral, and this will not give any contribution. Or we can just, well, we can say like this, and then everything just vanishes identically. So it will be 0 together with another together with time derivative of it. right? Because the argument of this function is minus t uh, uh, minus something uh, uh, that is greater than minus t. So this is always, oh, we can shift this integral in t from 0 to plus infinity, and then it will be like this. It will be g of minus t prime, and here it will be uh, minus t plus t prime. So let me write it separately like this. Maybe it is more a bit more understandable. Dt prime, dx prime. Sorry. Mm-hmm.
You said that you can easily show that if G is always non-zero, then the primary condition are violated. But I can see why.
No, but if it is non-zero, there is just no reason for this integral to vanish. You can choose some function which is a delta function, and it will give you this green function precisely at this point where it is non-zero. So it's easy to show that there are problems. This, yeah. Let me check. Yes. Okay. Can we go? Okay. Ah. Okay. Welcome. Uh, Yes, so we are looking for such function which solves this equation and has these conditions. And in principle, we know the form of its Fourier transform. The only question is how to take inverse Fourier transform. So let us try to write naively. G of tx is equal to what? To integral d omega over 2 pi dp over 2 pi e2 minus I omega t plus I px 1 over minus omega prime plus p prime. And we meet precisely this pose on the real line. So there is a integral over, so it's in principle it is from minus infinity to plus infinity. But let us draw the contour uh, in the omega plane. So it's omega plane, and we see this two poles at minus absolute value of p and plus absolute value of p. We also studied the functions which are analytic in the upper half plane or in the lower half plane. Their main property was that they vanish for a positive value of argument or for negative value of argument. And now we want a function which vanishes for the negative value of t. Uh, if t is negative, then it means that we can close, we should be able to close this contour in the upper half plane, because in this case, omega will be I times something times I. It will be something positive, and this will be something negative. So this contour should be chosen in such a way that all singularities are in the lower half plane. So it tells us that we can try to use this contour. So it's kind of additional definition of this green function, because when we write this formula formally, we get any solution of this equation. So in principle, it should contain all such solutions that correspond to these two poles. We will see it later, probably, that they correspond to these poles, but it is true. So we need to choose, we need to make some choice here. And our choice is to say that a contour of integration should be chosen in this way. Or we can alternatively say that this gain function is a Fourier transform of some function with poles shifted a little bit to the to the lower half plane. So it will be some absolute value of minus absolute value of p minus I epsilon, and this will be plus absolute value of p minus I epsilon. So in this case, this green function will be defined for the original contour for original integration contour, but then we will need to take a limit, right? Uh, so. Hmm?
Piccolo centro, però il punto è che qua non funziona. Non dovrebbe funzionare perché la funzione che ha non c'è tipo deve andare a 0 o moltiplicata per 0 in quel punto. Sì, cioè hai delle condizioni per applicarlo. Penso che ci siano, penso che poi non ci siano, però adesso vediamo che clic ci tra poi. Ok, thank you.
Okay. So. Hmm? Hmm. We will use it in any case. I'm just saying that if we use this Jordan lemma for such integration contour for negative time, it will it will give 0. So if we close a contour in this direction, then this integral for this. So this what they are. So here we were deciding which contour to choose, and we have chosen it in such a way that for t less than 0, this integral equals to 0. So uh, So if t is less than 0, then this exponential decays in the positive imaginary direction. So omega is minus. So e to minus I omega t. So let us substitute omega equals to I, and t equals to minus 1. Omega equals to some IR. IR t equals minus 1. So in total, it will be e to minus r. So it decays in the positive direction. So this contour. So for negative time, we can close this contour here and say that it is 0. And for positive time, we will close it below, and we will have a contribution from these two poles. So is it fine? So let.
Dicevi, al breve del tempo, quello che hai che per t meno di 0 se regoli il coefficiente superiore, cioè il segno superiore, viene 0. E l'ha dimostrato. C'è 0. No, è perché quello che cade come era violette, quindi questo è come il fenomeno di Jordan, quello là, le cose di Caverno, quindi vedi questo mi pare la legge non c'è, sono tutti a 0. Sotto invece il contributo dei due poli e adesso lo calcola. Quindi effettivamente si fa con il fenomeno di Jordan.
So is it fine? So for positive t, so for positive t, we can call this contour in the negative imaginary direction because this exponential goes to 0 in that direction. So for negative t, it is just 0. For positive t, it will be minus 2 pi I times sum of two residues. So it will be minus 2 pi I times 1 over 2 pi squared. And now we need to compute this two residues. So first, this residue, it will be I to minus 2 plus I omega absolute value of p plus I px divided by, so here we will have minus, oh, sorry, it is not omega but t. So, and here we will have minus 2 times the value of omega, so minus absolute value of p. Plus minus 2 times plus absolute value of p for another contour. So like this. So let us continue these computations somewhere else. So, so we can write, if you write this about both parts of this formula, then we can also take into account this negative time part and write that it is a heaviside theta of t, so in a sense it vanishes for negative t, times all these terms. So let us count the number of signs. It is minus 1, minus 1, minus 1, uh, uh, 3 times, and here there will be only 2 signs. So it is uh, I over 2 pi. Uh, so I forgot to write integral in dp.